Okay, so let's play around with a gas and derive the relation between the macroscopic quantities, pressure, volume, and temperature in what's called the ideal gas law. So we know what the concept of volume is. So let's say we have a box like that, and it therefore has some volume, V. There's nothing strange about that. We have a gas inside of that box. We notice we have some kind of gauge. We notice that there is a pressure on the sides of the box. So, right, we have here's one of the walls, and we notice that there's some pressure indicated by this arrow. So there's some force per unit area, and that's the pressure. Okay, so pressure is the force per unit area. We're not thinking about what's causing that force per unit area. It clearly has something to do with the gas. And then we can imagine touching the box and noticing that it feels hot or cold, and that sort of motivates the introduction of the concept of temperature T. Not in a very precise way, but then we can start to play around with things like thermometers, where we have some liquid, specifically mercury, and notice that when we put this into contact with the object, this mercury either rises to some level, and we notice a correlation between our sense of whether something is hot or cold and the height of this column of mercury. And so we get a sort of an idea of this additional quantity that we call temperature. And so, for example, if we have two boxes and they are the exact same volume, so we can imagine we're doing this experiment and we fill it with the same gas, but here we have a temperature T1 and here a temperature T2, and then we put them together, something like that, we'll notice that we get a temperature T3 here, and that temperature is related to the other two temperatures as the average. Okay, so each box changed its temperature. One increased, the other one decreased, and we got some intermediate temperature T3. Okay, so let's be a little bit more specific here, and let's imagine that we have the box on the left, so left box and right box, and the left box has, in addition to the temperature, T naught, it also has a volume that's specified as V naught. The other one on the right as well has that volume. We're not going to change that. And we measure the pressure, and its value is P naught. And then we do the same for the box on the right. And so we know the volume is V naught. And we measure the pressure, and let's say we get P naught over 2. And we measure the temperature, and we find it to be T naught over 2. And then we put them together like this. And so we have one box. We can sort of imagine putting them together kind of means getting rid of the wall in between the two. And so the gas in one can move freely into the other side. And then we make these measurements, and we find that the pressure is 3 P naught over 4. The volume is twice V naught. Well, for each box, it's still the same volume V naught. And now we find the temperature to be 3 T naught over 4 for each box. And so we can notice that, notice that if we look at this quantity pressure times volume, and we write it for the values before we put the boxes into contact, we get P naught V naught for this one, and for this one we get P naught V naught over 2, and that gives us a 3 P naught V naught over 2, and then we can do the same thing after we've put them into contact, and these values give us 3 P naught V naught over 4 for each box. So it's 3 P naught V naught over 4, and therefore we have 3 P naught V naught over 2. And notice that these two things are the same. And so there's something that's conserved. Well, what kind of a quantity is this? So maybe we can pause for a moment and notice that if we do combinations of, say, pressure and temperature, sort of aside, we have P naught, T naught here, and then we have P naught over 2, T naught over 2, right? That's P naught, T naught over 4. And so what do we get here? 5 P naught, T naught over 4. And then we do the same thing later. For this combination, we have 3 P naught over 4, 3 T naught over 4. Twice, right? We're adding them together. 3 P naught over 4, 3 T naught over 4, and that's going to equal to 9 halves P naught T naught. This quantity, whatever it is, isn't conserved. So what kind of a quantity is this? Well, let's look at it dimensionally. So dimensionally, pressure times volume is, pressure is force per unit area, so that's a length squared, force over length squared, times volume, that's length cubed. That's force times length, or force times distance. That's actually the definition of work. And therefore, we're talking about, of course, energy, because work is energy. Work equals delta K, as we know. So, so we have energy conservation. And so we can say that energy was exchanged between the boxes such that none of the energy was lost. So also notice that T, total temperature before, meaning we'll just do the same thing that we did here for temperature. For the box on the left, it's T naught. For the box on the right, it's T naught over 2. We get a 3 T naught over 2. And the T total after is equal to T naught. Let's look at this, right? The volumes are the same. T naught plus T naught over 2 divided by 2 for each box, but then we have to multiply that by 2 to do the same thing that we did here, and that gives us a 3 T naught over 2. And so what we see here, let's get another sheet. Is that this quantity P times V, which for the box on the left initially is P V naught, is related. It's the conserved quantity can also be written in terms of that T, but there's some constant, so we can say something like that. And then for the box on the right, we have P naught over 2 V naught equals C T naught over 2. And of course, we see that 3 P V naught over 2 equals 3 C T naught over 2. And so basically, this quantity is an energy. So energy is related to this concept temperature. There's some constant there. And so we've just motivated this relationship, which we call the ideal gas law, because we are ignoring some details about gases that don't behave in this way. So this is the macroscopic relation. This is the equation that relates to macroscopic quantities, pressure, volume, and temperature. And we know nothing about ultimately what's causing this and what's behind this.